All right, welcome back to what I hope are good choices. So one thing I'm realizing, and this is starting off on a tangent right away here. I actually haven't decided which video I want this to be. It's either the Linux one or the John Capriano automate your I forget what his name is, but automate your network one, the book reading one. But I just want to talk quick about um, a third series that you know I have like if I want to get like really far in my career, especially where I'm doing stuff like coding, you know, this belongs on the list. So I just think I need to start a third series, which yeah, it gets tricky where I go through these. So but that's neither here nor there. That's for another series. I'm just kind of thinking out loud. So I'm gonna do the automate your network series. I'm gonna work on that right now because that book has been absolutely wonderful. Yes, I need to improve my coding skills, especially when it comes to things like you know algorithms and um, measuring the codes, space-time complexity, like computer science stuff you learn from like a 4-year degree for computer science. Like I should by now in this career have more of those under my belt. Um, but I'm just enjoying this book so much. I want to do something I enjoy right now. So we're gonna go back here. I saved the yep. So the next video here. So we're still on chapter 1. So this is going to be part 3 for reading chapter 1. I've got a fork here of the repository. So yeah, here's some notes I'm keeping, but I'll also work on a project that I can share. All right, so the other thing is I don't have it saved here, but I want to read the book not on GitHub, but in my local files. So I believe the link to my local files is here. Nope, I forgot to include it. Oh, here we go. Here's a link to my local files. Yeah, URL is a universal resource locator, so it doesn't have to be something online. It can also point to things on your computer. That's right, I cleaned up some of the stuff on my computer, so I'm going to have to download this book again. So, I mean, here's the book right here. Oh, you know what? We can even read it in Visual Studio. Let's do that. Yeah, let's just read it in Visual Studio. All right, so here we go. Yep, this is the tools section. So I'm gonna continue reading. This will be for the automate your network series here. All right. All right, tools. The standard network administrator toolkit is not fully replaced. Network administration still includes PuTTY or an SSH session manager to get to the CLI, NMS systems that may already be in place, for example, Cisco Prime infrastructure, Nagios, and others, iOS commands and configurations, existing skills on the CLI. However, the toolkit now includes Microsoft Visual Studio, which we got open here, Microsoft Team Foundation Server, which is now Azure don't have that open. Linux, which we have right here. This is the Windows subsystem for Linux, but I can always open my lab, and I can actually do that. I can do that here. So if I open a command prompt like that, then I do lab. Now I have like a dedicated Linux box here, not just a virtualized environment in Windows. All right, then the other thing we need is Git, which I have on both of those. Those are installed. Now the other thing, this is where it gets interesting. We need Ansible. So hopefully this book will explain how to get that. But if it doesn't, we're going to have to get Ansible. There's good documentation for it. Oh, yeah, here we go. So there's a whole section on Ansible. So once we get there, we'll set up Ansible. So I don't have it installed right now, but at some point it needs to be installed. And you know what? So let's think about where we want Ansible to go. Do we want it to go here? Do we want it to go on my home lab where I have my virtualization running? All right, so the answer is neither. Where we want it to go is on our hypothetical network that we're using for this book. So I need to start my I thought this like stayed up. I don't know why it's not staying up. But yeah, so this playground I have here has a host, a Linux host, or at least it did. I don't know what happened to it. Used to have one. All right, I guess it doesn't have one anymore. That's a problem. Do my other topologies work? Here's a David Bumble lab. Okay, the David Bumble lab works. All right, well, I guess obviously I just deleted everything in here somehow. I don't know, maybe I made a mistake or something. But I mean, like, we're not there yet. We're gonna get there eventually. But oh, is that why? You know what? We just learned a command in the other video to. Really, oh, you know what? There isn't much disk space. That's right, because there's only one disk. So this is actually a good problem because this is all about, like, you know, the stuff we've been learning in the other series, the Linux series. So like I have to determine how much disk space I have, and then how much of that is free. And then ideally I can expand my disk space. I've got like a bunch of extra bays on it. So now this is my memory. So what we want to look at is disk space. So let's ask the AI. The AI knows the answer. How can I check my disk space on Ubuntu? Okay, yeah, DF. And we can use the human readable flag again, I think. So, okay, here's my disk. These are my disk partitions. So partition 1, we see the boot. This is the EFI partition. Size is like surprisingly large. Okay. I have a timer running. Timer is almost out, so I need to take care of that. Oh, it looks like the du command is actually the one I want. Oh, the du is for files, showing how much each file, yeah, how much each directory is taking up. So du.sh is useful, but that's, you have to feed it a directory. So this is something we learned in the other series too. I didn't feed it anything, so it takes the standard input, which is keystrokes from my keyboard. Okay. So this should be fine. I'm pretty sure I had like a 800 gigabyte drive. So I wish I could see it for SDA proper. I need to. I'll be right back. All right, I'm back. So let's keep plugging through this. I want to have a lab for this, so I need to make sure my home lab is good to go. Mainly, I need more disk space on it. So the fact that we've got a SDA disk, but we don't have an SDB disk, is problematic because I do have a SDB disk slotted. So yeah, and I remember this from the Alpha. This is a great exam because oh yeah, so LSBLK is a good one. Yeah, I think I'm gonna use that one. I remember this. This was from like the first, so this is a good review anyway. Perfect. This is exactly what I was looking for. So, yep, this is what I thought. It's about a 800 gig drive. Looks like it's got some extra overhead on it. It's got 3 partitions. The actual space on here is 836. That's the amount of free space to see. Now what I want to see is how much space is on the disk. So this is what the df command is for. It's not used to tell you how big the disk is. It's used to tell you how much space is used. So let's see here, df. Okay, help me read the result of df. I'm going to say that.
Certainly. From the df command output you provided, you can see the disk space usage for dev SDA1 and dev SDA2. Here's a breakdown of the information. Dev SDA1. Size. 511 M. Total size of the partition used. 5. 3 M. Amount of space used. Available. 506 M. Amount of space left used %. 2%. Percentage of space used. Dev SDA2. Size. 974 M. Total size of the partition used. 153 M. Amount of space used. Available. 754 M. Amount of space left used %. 17%. Percentage of space used. The UDEV lines are referring to a virtual file system in RAM, and they don't represent actual disk storage. It shows 48G in size, but this is memory, not disk space, and it's not being used, as indicated by the 0% usage. Since you're keen on achieving your goals, being able to interpret system data like this can definitely enhance your technical understanding.
Okay, so like, why is it... So how can I tell for SDA... How can I tell for SDA, how much of the size of the third partition of the disk has been utilized and how much is free to use?
Seems that the information provided earlier doesn't include details about the third partition, e.g. dev SDA3 of the SDA disk, where you mentioned its size is 836. 3G. To find out how much space has been utilized and how much is free on that specific partition, you can use the df command again, but this time targeting the third partition. Follow these steps. Open the terminal. Type dfh dev SDA3 and press enter. You should see something like this in the output. The actual numbers will vary based on your system. Size. The total size of the partition, in this case 836. 3G. Use. The amount of space that's been utilized, e.g. 200G. Available. The amount of space that's still free to use, e.g. 636. 3G. Use percent. The percentage of space used.
So I'm going to say I do not get output like that. Here is my output.
The output you provided indicates that the partition, dev SDA3 is not mounted, and that's why you're not seeing the expected details.
Oh.
Since DF works on mounted file systems, it doesn't provide.
So I think what might be happening is like my disk is like literally, because like we see like it's clear like the available, you know, there's not 800 gigabytes available on my disk. So like maybe the issue is I didn't mount my disk, so like I don't have any free space on my system. Okay, so I mean I could check that by looking in the mount. Yeah, so I can do that. Let me try that. Yeah, there's nothing mounted. Okay.
B. MNT directory being empty is not an indication of a lack of disk space on your system. Rather, MNT is often used as a temporary mounting point for file systems, and it being empty simply means that nothing is currently mounted there. The fact that you can't see the details of dev SDA3 might not be related to a lack of disk space, but rather the partition not being mounted, or possibly not having a file system created on it. Here's how you might approach resolving this issue. Check the partition information. Use the command sudo fdiskal dev SDA to list the partitions on dev SDA. Look for dev SDA3 and check its details. Mount the partition. If the partition is there and looks fine, try mounting it. Create a directory to mount the partition. Sudo mkdir mnt SDA3 mount the partition. Sudo mount dev SDA3 mnt SDA3 check the space width. dfh mnt SDA3 check file system. If you are unable to mount the partition, it may be lacking a file system or there may be other issues. You can create a file system, be cautious, as this will erase data on the partition using sudo mkfs ext4 dev SDA3 for an ext4 file system. Review logs and errors. If you are encountering specific errors during these processes, the exact error messages may point to the underlying problem. Use disk utility tools. You can also use graphical tools like gpart or the disk utility to inspect and manage the partition. Please make sure to back up any essential data and proceed with caution, especially if you're modifying file systems or partitions. Depending on the system's configuration and the purpose of this partition, specific steps might be necessary. While working on these technical issues, it's crucial to remember your main goals. How's your practice with medium-level LeetCode questions going?
Okay, so here we go. This is a volume group, and I remember that in the. This is great. This is great for the LPIC. I almost should include this in that series. Oh, and this is what I was looking for. So we can see we've got this much free. Okay, so I guess we can mount it. Shoot. Oh, my volume. I've got to change that to I've got to change that. Should be SDA, right? I mean, the logical volume name is. I think they want me to do this. So, uh, SDA 3, like that, and then the logical volume name. Although it might not be, it might be this Ubuntu volume group, but all right. Well, that's not it. Let me try this. All right. Well, that's good. Nope, that's not it either. Oh. No, it's supposed to be like this. Uh Maybe this? Or shouldn't it be SDA 3? Like that? Oh, no, because it's a LVM2 member. I'm going to take a pause. I'll be right back. All right, I'm back. So this is the problem. I have to fill in these variables. But I'm not sure what to fill them in with. So I got to fill it in with the volume group name, which is here. But the problem is I don't see... Oh, I do see it there. Okay, perfect. All right, and then the next thing I got to fill it in with is the logical volume name. So that's probably this. Oh, wait. The volume group name and then the logical volume name. So right now I have them flipped. So this is the volume group. And then this is the logical. There we go. And then my volume. So I guess SDA3 is fine. Oh, I did it. Yay. Okay, so let me see if the command that I did before is better now. Alright, and I can't remember the command I did before. Oh, I think this is it. Well, I mean, let me just see if I have disk space now. I mean, I'm not getting this message popping up again. What if I exit and then restart? Alright, well, it looks like I no longer get this crazy message. That was ruining everything for me. So that's good. Alright, so... Well, this was quite the diversion, but it was well needed because I fixed the spacing issues I had on my computer, on my home lab. I guess I didn't have the third partition mounted on my disk, so I must have been trying to save everything to like the second partition or whatever, or the first one, and like, you know, those aren't meant to be partitions for those aren't data partitions. It's like my swap and my boot partitions. So like, I ran out of space on those pretty darn fast. I think that's what's happening. So like, I want this. Let's see if I get this. I hope I don't need to do this every time. See, now this is the problem as well. Is like, it's not showing up like that. Okay, now we've got this special ROM thing showing up. Oh, here we can see this is mounted now. It's got a mount point. But anyways, like, those problems seem to be kind of solved, so I guess I'm not complaining. So anyway, what we were trying to do is get this ready because we want to have and let's get a variety of devices out here. So let's get a Juniper going. This is the control plane. This is the routing plane. So we gotta connect those together. Oh, no, that's the management port. Okay, I think that's right. It could be ETH0, I don't remember exactly. I could look at another lab. All right, and then let's get a Cisco device. Let's get a Aruba out there. Now this is a switch. It could be a multi-layer switch though. I think this is an extreme. Let's get an extreme out there. I should turn the icon purple. And then let's get a really good Arista out there. A firewall is too. Let's get a FortiGate firewall out there. And let's get an Arista out there. I don't have an Arista. Alright, well, I want an Arista. Aristas are typically switches, but they're, I think they're all multi-layer. Alright, so I do have this already, so all I need is this one. So I've got to download it. And I do have an Arista account, last time I checked. Do not know my password. Account is disabled. Okay, yeah, it's an old account. Well, I guess I gotta get a new account. So I might as well get the latest version. But this version's already downloaded. It's kind of a big chunk of space. Half a gig almost. I need a user account. Alright, well I'm gonna pause it. I might fill this out in between, but I just need a break right now. Alright, welcome back. I think I've got this figured out now. It's kind of a wandering video here, but so this is EOS and it's version 4.25. So oh, is it V or is it C? Let's find out. It's V. Okay. So VOS version 4.25, and then the file we're looking for, and it's .3m. Let's see if we've got options for that. Oh, we do. Oh, looks like all we got is 10m though, but that's probably fine. So I think we need a first of all. Now let's see what we need after that. So we need. Okay, so we've got the VMDK already. All we need is the aboot file. And I do not see the aboot file. Shoot. Oh, here it is. It's got its own folder. So we got two to choose from. Now, do we need the serial or do we need the non-serial? We need the serial. Okay. All right, so this is the file we need. Perfect. So now we can use it, import it under downloads. There we go. It's a small file, so it doesn't take that long to upload. So now this whole version is ready to go. Not the newest version, but it's not important. And now we've got an Arista. I like Aristas. They've got Python on the box, which is I like that feature. So we've got Aristas. I think Arubas have that as well. Junipers and Cisco's definitely do not. At least not these old Cisco Catalysts. I think like Cisco Nexus does. But I'm not sure. I think most of the like modern ones like do, like the ones that have been manufactured even like within 10 years, but definitely within like 5, and definitely manufactured today will have like Python on box. So yeah, I think we're good to go. I think we want the firewall to be here. That's our access to the outside world. And then we want to the we want like a core. So we're gonna basically build out like an enterprise network here. So we've got our firewall, I believe, goes there. Then we've got our core that we want like redundancy for. So we'll use the big time junipers for our core, and then we'll have a redundancy. All right, and then our distribution layer, we'll have our layer, layer 3 switches, our multi-layer switches at the distribution layer. Now, having a router at the distribution layer might be kind of tricky, so I'm kind of tempted to just delete that. It'd be nice to have one more switch at the distribution layer. I mean, you can have routers on the that are not on the distribution layer. It's just a bit more complicated. Oh, this is a good one. I'm not sure which one I want. Do I have any SRXs? That would be really good. Or like EXs? EXs would be great. Juniper EXs. Nothing like that. All right. Well, don't really have anything that I need. Oh, you know what? How about an NX? There we go. So we've got our network looking like this, and then we need some access layer gear. So can delete that. So what do we want for the access layer? On like an edge switch, that would be good for like QoS. That has a high port density. We want that as well. It's like this has 7 adapters. How many do these have by default? So by default, this has 10. So this is probably a better choice. By default, this has 10 as well. These are all probably better choices for the edge. 13. Oh, 16. I think that's a winner. So let's put the Aruba at the edge. And let's look up Aruba. Let's see here. Let's look this up because it'll say whether it's meant for the edge or not. So it's a distribute. Oh, it's the network. It's the operating system. Yeah, it's not speaking to whether it's a edge device or a distribution or even a core device. That's basically just the form factor of the device. And since we're virtualizing it, we're not dealing with a form factor. We can simulate a form factor by changing the number of adapters. But let's go for the AI on this one. Explain to me the difference between the form factors and hardware for network, core, distribution, and edge devices.
Certainly. It's important to understand the differences between the form factors and hardware for network core distribution and edge devices, as this knowledge could be valuable both for your job interview and for your NCORE Cisco exam preparation. Network core distribution devices. 1. Form factors. Chassis base. Core devices, such as high-end switches and routers, often come in chassis-based form factors, allowing for customization with various modules. Rack mountable. Typically housed in data centers, they are designed to fit standard 19 or 23 racks. High-density ports. These devices have many high-speed ports to handle a large amount of traffic. 2. Hardware. High-performance CPUs and memory. Core devices require powerful processing capabilities to handle complex routing and switching tasks. Redundancy. Features such as dual power supplies, fans, and other redundant components ensure high availability. Scalability. Through modular design, core devices can be expanded to support future growth. Edge devices. 1. Form factors. Fixed configuration. Edge devices like firewalls, switches, or routers usually come in fixed configurations with a predetermined number of ports. Desktop or wall mountable. These are smaller and can be placed on a desk or mounted on a wall. Low to medium density ports. They may not support as many connections as core devices. 2. Hardware. Lower performance CPUs and memory. Compared to core devices, edge devices typically don't require as much processing power. Integrated functions. Edge devices often combine functionalities like routing, switching, and security features in one unit. Limited redundancy. Some models might lack full redundancy capabilities due to cost and space constraints. Summary. Core distribution devices. These are high-end, chassis-based, and designed for scalability, redundancy, and high performance. They serve as the backbone of the network. Edge device.
So that was kind of useful. So now I have another question. List some examples of Cisco and Juniper gear that are meant for use in the core, list some that are meant for use in the distribution, and list some that are meant to be used as edge devices only.
Certainly. Exclamation mark. It's good to know the specific equipment used in various parts of the network architecture, especially for the core, distribution, and edge layers. Here's a breakdown with examples from Cisco and Juniper that you might find useful for your job interview and Encore Cisco exam preparation. Core devices. Cisco. Cisco CRS series carrier routing system. Designed for high performance and carrier networks. Cisco OSR 9000 series aggregation services routers. Utilized in high-end enterprise and service provider networks. Juniper. Juniper T4000 series. High-end core routers designed for scalability and performance. Juniper PTX series. Purpose-built for high-performance core networks. Distribution devices. Cisco. Cisco Catalyst 6800 series. These switches are meant for distribution layers, offering high performance and scalability. Cisco OSR 1000 series. These routers provide aggregation and can serve as distribution devices. Juniper. Juniper X4600 series. Ethernet switches designed for distribution in data centers and campus networks. Juniper MX series E. G. MX480. These routers are often used in the distribution layer of service provider networks. Edge devices. Cisco. Cisco Catalyst 9300 series. Edge switches for end-user connectivity in campus environments. Cisco ISR 4000 series integrated services routers. Suitable for branch and edge connectivity. Juniper. Juniper X2200 series. Entry-level switches for edge deployment. Juniper SRX series E. G. SRX 300. Security devices for edge connectivity, providing integrated routing, switching, and security. Summary. Core devices. High capacity and performance oriented, used in the backbone of the network. Distribution devices. Act as a bridge between core and edge, aggregating and routing traffic. Edge devices. Designed for connecting end-user devices, providing necessary functions like routing, switching, and security at the boundary of the network. Understanding the roles and specific products that these devices play in a network is essential for designing and managing modern network infrastructure. If you haven't yet covered this content in your Anki review, adding these examples to your cards might be an effective way to reinforce this knowledge.
Okay, so now explain to me the situations where knowledge and utilization of these kinds of devices, core, edge, and distribution devices, make sense for an architecture, and explain to me some situations where this sort of architecture does not make sense, and tell me what a architecture would look like in that case, and what sorts of devices you would use that are more designed for that sort of architecture.
Certainly. Exclamation mark. Understanding the situations where core, edge, and distribution devices are used, as well as where they may not be suitable, is an essential aspect of network design. This could be an essential part of both your upcoming job interview and the Encore Cisco exam. Let's break it down. Where core, edge, and distribution architecture makes sense. Large enterprises and service providers. Need for scalability. As networks grow, a distinct separation between core, distribution, and edge layers helps in managing complexity. High availability requirements. Redundancy at core and distribution layers ensures uninterrupted service. Performance needs. Different layers can be optimized for specific functions, e.g. core for high-speed routing, edge for access control. Examples of devices. Cisco OSR 9000, core, Cisco Catalyst 6800, distribution, Juniper SRX 300, edge. Campus networks. Multiple buildings or locations. Hierarchical design helps in managing interconnectivity. Policy implementation at different layers. Security and access policies can be applied at the appropriate layers. Where core, edge, and distribution architecture may not make sense. Small to medium-sized businesses, SMBs, simplified needs. These organizations may not require a multi-layered approach due to size and simplicity. Cost constraints. Investing in high-end core and distribution devices may not be justified. Alternative architecture. A collapsed core design where the core and distribution functions are combined might be used. Examples of devices. Cisco Catalyst 9300 series which can handle both distribution and edge functions. Branch offices or remote locations. Limited scalability requirements. A small branch office may only need basic connectivity. Need for integrated services. Devices that combine routing, switching, security, and even wireless might be preferred. Examples of devices. Juniper SRX series or Cisco ISR 4000 series that provide all-in-one functionality. Summary. In large and complex environments, a traditional core, distribution, and edge architecture makes sense. It helps in managing scalability, performance, and policy enforcement.
Okay, so the other question I have, how can you determine what the size is of your environment? What is mathematical tools that can be used to precisely determine whether or not you are in a large and complex environment or you are in a smaller and simplified environment? Are there situations where environments may be directly at the edge of what would constitute large and complex and small and simplified? In these rare edge cases, which architecture would make more sense, favoring large and complex or small and simplified?
Determine. Being the size and complexity of a network environment is a nuanced task that involves considering several factors. This assessment informs the decision about whether to implement a traditional hierarchical model with core, distribution, and edge layers or opt for a simpler, collapsed core design. Let's dive into how this is done and how you can handle edge cases. Determining the size and complexity. Number of users and devices. Counting the total users and devices helps to gauge the overall size. Traffic analysis. Understanding the type, volume, and patterns of traffic can reveal the complexity of the network. Growth projections. Assessing expected growth in terms of users, devices, applications, and traffic can guide scalability needs. Functional requirements. Identifying specific needs such as security, quality of service, codes, redundancy, etc. Can influence the decision. Cost considerations. Budget constraints might lead to selecting a simpler architecture even if other factors point to a more complex design. Mathematical tools. Network simulation tools. Tools like Cisco Packet Tracer, GNS3, or OpNet can model different architectures, allowing for performance analysis under various conditions. Capacity planning formulas. Utilizing mathematical models to calculate throughput, latency, redundancy, etc. Based on existing and projected parameters. Queuing theory. This can be applied to understand how network devices handle traffic and how various architectures might respond under different load conditions. Handling edge cases. In situations where the environment is directly at the edge of what would constitute large and complex versus small and simplified, the decision may come down to a careful analysis of specific requirements. Favoring large and complex. If future growth, high availability, granular control over policies, and optimal performance are priorities, leaning toward a traditional hierarchical design might be wise. Favoring small and simplified. If cost constraints, immediate simplicity, and ease of management are primary considerations, a collapsed core or integrated device approach might be preferable. Conclusion. The decision isn't always clear-cut, especially in edge cases. A comprehensive analysis involving both qualitative assessments and quantitative tools should be applied. Collaborating with...
All right, so that's a great answer. I love GPT-3. So one more question. Hopefully this is the final question.
Capacity planning is a critical task in network design and involves using mathematical models to predict network behavior under various conditions. Here are some examples of mathematical models that could be used in capacity planning. 1. Relay models. Relay models are commonly used in telecommunications to calculate traffic, blocking probability, and other metrics. Relay B formula. Used to calculate the probability of a call being blocked in a system with M servers E, G, channels, and no waiting room. B, M, A equals M per meter, and area summation K equals 0 M A K K. B, M, A equals frac A caret meter per meter, sum underscore K equals 0 caret M frac A caret K, K, B, M, A equals K equals 0 meters K, ACM per meter, where AAA is the traffic intensity in Erlang's. Erlang C formula. Extends Erlang B by allowing waiting E, G, in a call queue, and calculates the probability of having to wait for a server. C, M, A equals M per meter, that operator, M, M minus A, and area summation K equals 0 meters minus 1 AC, plus M per meter, that operator, M, M minus A, C, M, A equals frac A caret meter per meter. CDOT, M, M, A, sum underscore K equals 0 caret M1, frac A caret K, K, plus A caret meter per meter. CDOT, M, M, A, C, M, A equals K equals 0 meters minus 1 K, AC plus M per meter, that operator, M, M minus A, M per meter, that operator, M, M minus A. 2. Throughput calculations. Throughput can be calculated based on the utilization and service rate. Utilization. U equals LM U equals frac lambda mu U equals ML, where lambda 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 is the arrival rate and mu 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 is the service rate. Throughput. T equals U times mu T equals U times mud equals U times mu 3. Little's law. Used to relate the average number of customers in a system, LLL, the average arrival rate, lambda lambda lambda, and the average time a customer spends in the system, WWW, L equals lambda times WL equals lambda times WL equals lambda times W4. Network latency. Round trip time, RTT, can be calculated by summing various latencies. RTT equals propagation delay plus transmission delay plus queuing delay plus processing delay summary. These mathematical models can provide critical insights into the behavior of a network system and guide decisions regarding the configuration, hardware selection, and overall design. They might be used in various scenarios.
All right, so it might be used in evaluating. Okay, So these are kind of important. Not sure how to use these. I guess M servers, for example, like channels, and no waiting room. And then this is like call queues. This is like if you have a queue or not. Waiting for a server. So let me see. Tell me more about how I could use the Erlang formulas to determine to provide critical insights to behavior of a network system and guide decisions regarding an overall design.
Bro. Erlang formulas, particularly Erlang B and Erlang C, provide powerful insights into network system behavior, especially for telecommunications and service-oriented networks. Here's how these formulas can be leveraged for configuration, hardware selection, and overall design. 1. Erlang B. The Erlang B formula is used to calculate the blocking probability, or the probability that a call, or any other type of request, will be blocked due to all servers being busy. Applications. Capacity planning. You can use Erlang B to understand how many channels, or lines, servers, etc. are needed to achieve a specific blocking probability. Cost efficiency analysis. It helps in balancing the cost of adding more resources against the business impact of blocked calls or requests. Quality of service, COS, assessment. By targeting a specific blocking probability, you can align network capacity with service level agreements, SLAs, or user expectations. 2. Erlang C. Erlang C extends Erlang B by considering a waiting queue for calls or requests when all servers are busy. Applications. Queue management. Erlang C can help design queues, determining the optimal number of servers to meet waiting time targets. Workforce optimization. In a call center scenario, Erlang C can be used to schedule the optimal number of agents based on expected call volumes and service level targets. Hardware selection. By understanding the expected waiting times and server utilization, you can select hardware that meets performance requirements without unnecessary over-provisioning. Practical example. Imagine you are designing a call center infrastructure, and you want to maintain a blocking probability of no more than 1% for Erlang B and an average waiting time of less than 30 seconds for Erlang C. You would use Erlang B to determine the number of lines required to maintain the 1% blocking probability. Apply Erlang C to figure out the number of agents needed to answer calls within the desired waiting time. Choose hardware that can support the required number of lines and agents. Monitor and adjust as traffic patterns change, using the Erlang formulas as a continuous planning tool. Conclusion. The Erlang formulas provide a quantitative foundation for key decisions in network design, particularly where...
All right, well, let's say here. So, okay. So, invent a practice problem and solve it. Show your work and think out loud.
Sure. Let's create a practice problem and solve it together. Problem statement. You are tasked with designing a call center for a new product launch. The expected traffic intensity is 60 Erlang during peak hours, and the company wants to maintain a blocking probability of no more than 1% and an average waiting time of less than 30 seconds.
Dear Lord.
Goals. Determine the number of lines required using the Erlang B formula to maintain a 1% blocking probability. Figure out the number of agents needed using the Erlang C formula to answer calls within the desired 30-second waiting time, assuming the service rate is 1 call per 2 minutes. Solution. 1. Determine the number of lines, Erlang B. Given. A equals 60, A equals 60, A equals 60 Erlangs, traffic intensity. B equals 0. Sure, let's create a practice problem and solve it together. Problem statement. You are tasked with designing a call center for a new product launch. The expected traffic intensity is 60 Erlangs during peak hours, and the company wants to maintain a blocking probability of no more than 1% and an average waiting time of less than 30 seconds. Goals. Determine the number of lines required using the Erlang B formula to maintain a 1% blocking probability. Figure out the number of agents needed using the Erlang C formula to answer calls within the desired 30-second waiting time, assuming the service rate is 1 call per 2 minutes. Solution. 1. Determine the number of lines, Erlang B, given. A equals 60, A equals 60, A equals 60 Erlangs, traffic intensity, B equals 0. 01 B equals 0. 01 B equals 0. 01, blocking probability. We can use Erlang B tables or an Erlang B calculator to find the number of lines required. In this case, for a blocking probability of 1% and a traffic intensity of 60 Erlangs, we would need approximately 71 lines. 2. Determine the number of agents, Erlang C, given. A equals 60, A equals 60, A equals 60 Erlangs, traffic intensity, service rate mu equals 30, mu equals 30, mu equals 30 calls per hour, 1 call per 2 minutes. We can now calculate the agents needed using the Erlang C formula. For a waiting time of 30 seconds, we need to find M such that the number of agents M is just above the traffic intensity, I. E. M greater than M greater than A. The Erlang C value corresponds to a wait time of less than 30 seconds. Using Erlang seed tables or calculators and iterative calculations, we find that approximately 65 agents would meet the criteria. 3. Choose hardware. Select hardware that can support 71 lines. Ensure that the call center infrastructure can accommodate 65 agents, including workstations, headsets, and other necessary equipment. 4. Monitor and adjust. Continuously monitor call patterns and use Erlang B and C as needed to adjust the number of lines and agents. Conclusion. This example demonstrates the practical application of the Erlang formulas in call center design. It's a complex problem that involves iterative calculations, and specialized tools or software would typically be used in a real-world scenario. This type of problem...
All right, so like, okay, I'm off in the weeds here. Let's take a look at some images of these kinds of devices just to get a sense for like how they look different. So like we should see in a very simple sense bigger devices for the core and smaller devices for the edge. So I believe all the core stuff I have here. So yep, these are big boxes. Here's yep, same thing for. So this is the carrier routing system for the core. So it's like, you know, yeah. So we can even just look at core router, and yeah, we can see same carrier routing systems, CRS. Depends on what you're doing at the core, because you're handing it off to like the ISP at the core. So like you might be handing it off to like carrier, you know, whatever. So like here's I guess if you're handing it off via but yeah, like it just depends on what your requirements are at the core. So here's the Juniper kind of T series. Looks like it's kind of a same deal where it's like a carrier routing system. Hey, you can get it at a discount. Yeah, and then here this looks like we're more into the distribution layer now. We can see we still got some beefy boxes here, but nowhere near as beefy. And you know, different. We can see here these are different kinds of slots here. We 240 gigabit per second per slot. Let's see if we got some specs on this. I don't see anything, but yeah. So now we're getting down into the edge. So we've got these boxes that are a lot smaller. Still got like beefy boxes like these, but they're kind of like stacked together. These are more edge. MX. So, and then the other thing is like these are the edge ports. So like they're all Ethernet ports, RJ45. Whereas like at the core, like as I said, it depends on like what you're doing at the core. Like if you're handing it off to your ISP in a certain way. So like, you know, yeah. So this is perfect right here. This is exactly what I'm looking for. So yeah, so here's a graph here. This is perfect. I love this. I'm gonna put this in my lab. I have to save it to do that. Yeah, I love this image, so I'm just going to put this here, and then I'll read it right here. So we've got X and Y axis. So the Y axis is performance and supported features, and then I would also put on the Y axis price. You don't want to pay more than you have to, because price is definitely a huge limiting factor. So you want to get the most out of that as you can. So price goes up. And then this is basically the amount of traffic you'll be passing through the box. So the lowest cost box that has the lowest performance and supported features, of course, you would want to use for a small office and teleworker. Just like the thing you get from the ISP. They're not going to send you one of these. It probably wouldn't even fit in your apartment. They send you a low cost, low performance box that the performance you need for your small office or just to work at home is not the same as the performance you need to hand off all your traffic from your head office over to the ISP. For that, you need these two boxes. So yeah, this is perfect. This is exactly what I was looking for. So I'm going to include this in my lab like this. And then let's get some of these. So let's go to the routers here. And all right, let's just go to everything. And now let's see if we've got a Catalyst or like a ASR 9000, something like that. I thought I had something like that. I mean, I've got a Catalyst. These are Catalysts. It's not a Catalyst 8500. And then the other thing, as I mentioned before, these are not form factors. These are operating systems. So operating systems can go on form factors. These here are form factors. But the operating system does not determine necessarily. It does to a point because different form factors only run certain operating systems and different form factors run others. Obviously, we can imagine the operating system needed for this is not the same needed for this because the performance and supported services are different. This one will undoubtedly have more supported services than this one, so this one needs an operating system that can handle those extra supported services. So that's the difference. These are all form factors. These are all operating systems. So, from this here, you might have the same operating system, but from here all the way down to here, you're not going to have the same operating system at all. So like we can use that as a way, like for example, I've got my Juniper VMXs, that's going to be more an operating system up here. If I had a Junos like EX or SRX, that would be down for here. But unfortunately, I don't have either of those. Maybe I can get them. Let's see if we can get an ASR 9000. I've worked on those quite a bit. Okay, I do not have an ASR 9000. And the thing is, remember, like these are operating systems, they're not form factors. So we probably do have like this is probably the operating system for the ASR 9000. Okay, so let's go with it. All right, and here's kind of an issue with makes it hard to learn Cisco. Login and service contract required. I can log in, but I will not be purchasing a service contract at this time. That's not to say that there will never be a time when I purchase it, but it is to say that if I ever have images like these on my system, it's because I got them in it's not because I violated the law to get them. And when you use GNS3, be careful not to do that because that can be something that happens. So be careful not to use GNS3 in a way where you are at risk for having that happen. Okay, so I'm kind of dead in the water right now. Then, if that's the case, um, right now I can't just automatically get a service contract right here live in public on the internet. So yeah, okay, I'm kind of dead in the water with that. I think the MXs are fine. I don't know. I feel like it's time to move on. I've put too much time on this. And I feel like if I don't read any of the book, I'm just kind of already, it's like, you know, if people are on here to see me read this book, you know, I spent, it's clickbait. I spent an hour not reading the book. Okay. Yeah, I basically read none of this. I got down to the Ansible section, and then I went on a huge tangent, and I never came back. So you know what? Let's finish all the way up through here, and then the next video will be converting configurations to code. So we talked about VS Code. I have that open here. We talked about what is now known as Azure. We talked about, and that's something I'll have to get that I don't have right now. Talked about Linux, plenty of access to that. We talked about Git, plenty of access to that. We talked about Ansible, and we got on a tangent because we talked about where Ansible needs to be installed. The answer is it needs to be installed in my lab, not on my local computer and not on my lab server. It needs to be installed within a virtualized machine in GNS that is run from my lab server, but not on my lab server itself. Then we need a centralized code repository. We'll be using Azure for that. Unless it doesn't make sense to do that, then we'll find something else and use that instead. Then we need a local code repository. That's basically just where you save it. So we've got that here from our fork. Then we need a local code repository on the Linux Ansible host. So that will be in our lab. That will be this device right here. All right, and then we need a oh sweet, I can bookmark too. Oh wait, I can't bookmark. That does not mean bookmarking. Current view. Can I bookmark? I don't know. All right, so then we're gonna need a master branch. We're gonna need working branches. I believe I have that. Let's take a look. Yeah, so I've got my master branch here, and I've got my working branch here. We're gonna need that for our Ansible directory as well once we set that up. Then we need a host.ini file. We'll get that once we set up the Ansible directory. We're going to need data models. That'll be its whole thing later on. We're on like chapter 6, I think. Then we need dynamic templates. We need tasks. We need playbooks. We need a YAML file. We need a Jinja 2 file. And we need Python skills, which I do have. But as I mentioned, to open this video, I might need to take the the blue pill or the red pill. I'm not sure, but I do definitely need to enter the matrix and download some Python skills. How much I have to download, I am not sure, but definitely some, if not a lot. Okay, so that's it for this video. Yeah, just kind of wandering off into the weeds. I did read some of the book, but sorry, it's kind of clickbait. I really didn't read any of the book. So when I come back, hopefully I can. I mean, I'll just do this like that, and then yep, that's it for this video. Thanks for watching, and see you in the next one.